Welcome back to the Deep Dive, everybody. Today we're going to be tackling a topic that I think a lot of chemists probably don't think about all that much, but it's a pretty big deal. It's just this idea of taking something that works really well in like a small flask in the lab, and then trying to scale it up to actually make a useful amount of material.
Yeah, the scale up problem.
Yeah,
It's a huge one and something that most chemists, will encounter at some point.
yeah, absolutely, and it's something that I've dabbled in a bit, but I'm really excited to kind of get your expertise on this because I think there's a lot more to it than just multiplying everything by 10 or 100 or
All
whatever.
right, it's not you can't just take your lab notebook and just increase all the numbers and expect it to work the same way.
Exactly, exactly. So today we're going to be digging into the nitty-gritty of reactor design and the challenges of scaling up chemical reactions.
Yeah.
And to kind of give us some real-world examples, we're going to be drawing heavily from the journal Organometallic Process Research and Development. That's OPR&D for those of you who like to use the acronym.
Which most people do in the field.
Yeah.
It's a great journal, covers a lot of very practical aspects of process chemistry.
Yeah, it's kind of like the go-to place for chemists and engineers who are really trying to take these reactions from the bench top to actual production. So we're going to look at some of those examples and see how they tackle these challenges because it's not always straightforward. All right, so where do we even begin with this? Like when you're thinking about scaling up a reaction, what are some of the first things that come to mind?
Well, you have to, when you're starting in the lab, you're probably working with pretty small glassware, right? So we've seen some examples in the OPR&D literature where they're using like 500 milliliter round bottom flasks.
Yeah, pretty standard.
Yeah, basic glassware. But pretty quickly, as you start to scale up, you have to think about what kind of reactor you're going to use.
Right, because the flask isn't going to cut it once you start, making kilograms of material.
Exactly. And the type of reactor you choose is going to depend a lot on the specific reaction you're doing. One example we've seen in OPR&D is cycloaddition reactions.
Right, and just for our listeners who might not be, super familiar with organic chemistry, cycloaddition reactions are basically where you have two or more unsaturated molecules, meaning they have double or triple bonds, and they kind of come together and form a ring.
Yeah, they combine to form a cyclic product.
Yeah, right. And so those reactions, depending on the specifics, they might require a certain type of reactor to really work well.
Absolutely, and
Yeah.
even at a relatively small scale, like when you're just going from that small flask to maybe a liter or two, you have to start thinking carefully about how you're going to control the reaction.
Yeah, things get a lot more complicated.
They do.
Yeah. And one of the things that I always found kind of interesting, or I guess maybe counterintuitive, is that heat transfer becomes like a huge deal
Yeah.
as you scale up. Like, why is it that it's so much harder to control the temperature when you have a bigger reactor?
Well, it really comes down to the ratio of surface area to volume.
Okay.
In a small flask, you have a lot of surface area relative to the volume of liquid that's in there.
Right.
And that means that heat can be transferred in and out of the reaction mixture pretty easily.
So it's like it's got a lot of contact with the outside world.
Exactly. But as you scale up, the volume increases much faster than the surface area does.
So it's getting more and more insulated as it gets bigger.
Kinda, yeah.
Yeah.
The volume is going up by a factor of the cube of the radius, whereas the surface area is only going up by the square.
Right. Right.
So that means that the ability of the reactor to exchange heat with the surroundings gets worse and worse as you scale up.
So all that heat from the reaction starts to get trapped in there.
Yeah, and that can lead to some real problems. You can get temperature gradients within the reactor.
Right. So some parts are hotter than others.
Exactly. You might have some areas where the reaction is running really hot, maybe even getting out of control.
Oh, that's not good.
No, not at all. And then other areas might be much cooler, so the reaction's going really slowly.
So you end up with like an inconsistent mixture.
Right. And that can affect not just the yield of the reaction, but also the purity of the product.
Right, because if it's too hot, you might start getting side reactions and all sorts of all sorts of junk.
Exactly.
Yeah, and I can imagine that, especially with exothermic reactions, that could be a really big safety concern, right?
Oh, absolutely. If you have a reaction that's generating a lot of heat and you can't get rid of that heat fast enough, things can get very dangerous very quickly.
Right, like a runaway reaction.
Exactly.
Yeah. So they talk about that a lot in OPR&D, right? Like
Mhm.
how to manage the heat.
Yeah, they emphasize the importance of careful temperature control,
Right.
and they give some specific examples. For instance, in one paper, they were making a benzofuran derivative, and they used reflux conditions.
Okay, so reflux is basically where you're boiling the solvent and then condensing it and letting it drip back into the reaction mixture, right?
Right, and that's a way to maintain a constant temperature.
Right, so it's like a self-regulating system in a way.
Right. Yeah, exactly. But even with reflux, you still have to be very careful, especially at a large scale. You might need specialized reactors with jackets that you can pump hot or cold fluid through.
Right, to kind of fine-tune the temperature.
Exactly.
Okay, that makes sense.
Yeah.
So it's not just about, throwing the chemicals together. It's about really managing the energy flow of the reaction.
Very much so.
Yeah, that's really interesting. Now let's talk about mixing, because I guess naively you might think that in a bigger reactor you just need a bigger stir, right?
Right.
Just more
Right.
power, more mixing.
You'd think so, but it's actually a lot more complicated than that.
Okay, why that?
Well, for one thing, the way that fluids flow in a large reactor can be very different from how they flow in a small flask.
Right, it's not just like a scaled up version of the same thing.
Oh no, you can get all sorts of weird flow patterns. And depending on the design of the reactor and the type of impeller you're using, you might have some areas where the mixing is really good,
Okay.
other areas where it's practically stagnant.
So some parts are getting, really well mixed and other parts are just kind of sitting there.
Exactly.
Yeah, that doesn't sound good.
No, it's not. Because if the mixing isn't uniform, you can get variations in the concentration within the reactor.
Right, so some areas might have a much higher concentration of reactants,
Exactly.
and that could lead to, side reactions or other problems.
Yeah, absolutely.
Yeah, and I remember, I think there was an example in OPRD. I think it was a paper by Gadamassetti and Braish.
Yeah, I know the one you're talking about.
Yeah, where they had this nitro reduction reaction, and they were having trouble with the catalyst.
Right, the catalyst was getting coated,
Yeah, it was getting coated with something, and they couldn't figure out why.
and that was directly related to mixing and solubility. They found that in their initial solvent system, the starting material and the product weren't very soluble.
Okay.
And so as the reaction was proceeding, the product was starting to precipitate out.
Ah, so it was like coming out of solution.
Exactly.
Oh.
And that was what was coating the catalyst.
Ah, I see.
So they had to change the solvent system.
So they basically had to find a way to keep everything dissolved.
Yeah. They ended up using a mixture of THF and water.
THF, so that's tetrahydrofuran.
Right.
Yeah. Okay. And that improved the solubility enough that the catalyst didn't get coated anymore.
Wow. So just that one change made
Yeah.
a huge difference.
It did.
That's really interesting. So it's like the very environment of the reaction changes when you scale it up
Yeah, absolutely.
because of the way that things are flowing and mixing.
That's really fascinating. Okay, so we've talked about heat transfer, we've talked about mixing. Let's move on to reaction kinetics, because I guess you might think that if a reaction takes let's say an hour in the lab, it would take roughly an hour in a larger reactor, maybe a little bit longer. But
You'd think so,
Yeah.
but it's not always that simple.
okay, why is that?
Well, the kinetics of a reaction, meaning how fast it goes, can be affected by all sorts of things.
Right.
Temperature, concentration, mixing,
Okay.
and all of those things can be very different in a large reactor compared to a small flask.
Right. We've already talked about how the temperature and mixing can be, less than ideal in a big reactor.
Exactly.
So I guess that means that the reaction could actually slow down quite a bit.
It can, yeah. And sometimes you have to adjust the reaction time accordingly.
So what might take an hour in the lab could take, several hours or even longer.
Oh yeah, absolutely. Yeah, there was one example in OPR&D where they were making a cyclic ester,
Okay.
and the reaction time was something like 20 hours.
20 hours. That's a long time.
It is, yeah. But that's what they needed to get a good yield and purity.
So it's not just about, making more of it. It's about making sure that it's still the right stuff.
Exactly.
Yeah, that's really important. All right, so we've kind of laid the groundwork here. We've talked about some of the general challenges of scale up. Let's get into some of those specific troubleshooting examples that we were talking about earlier. Those real world stories from OPR&D.
Okay, sounds good.
Yeah. So let's start with that nitro reduction that we were talking about before.
Right, so that was the work by Garmasetti and Braish.
Yeah, and they were having that problem with the catalyst getting coated.
Right. And as we discussed, the root cause of that problem was the poor solubility of the starting material and the product in the original solvent system.
Right. It was like coming out as solution and gumming up the catalyst.
Exactly.
Yeah. So how do they actually fix that?
Well, their solution was pretty clever. They decided to add some water to the solvent mixture.
Right.
They were originally using just tetrahydrofuran, or THF.
Yeah.
And they found that by adding, I think it was about 10% water,
Okay.
they were able to significantly improve the solubility of both the starting material and the product.
So it was like just enough water to keep everything dissolved.
Right, and that prevented the catalyst from getting coated.
Wow. So just that simple change made
Yeah.
all the difference.
It did, and it also allowed them to lower the reaction temperature.
Oh, really?
Yeah, they were originally running the reaction at 70 degrees Celsius.
Okay.
And they were able to lower it to 50 degrees Celsius.
It's a pretty big drop.
It is,
Yeah.
yeah. And that actually helped to further reduce the formation of impurities.
So it's like a win-win.
It was,
Yeah, that's a really good example of how, sometimes the solution can be kind of unexpected.
yeah,
It's not always obvious what's going to work.
absolutely.
Yeah, that's really cool. Okay, what's another example of a real-world problem that they tackled in OPR&D?
Let's see. Oh, there was a good one involving the quenching of a reaction.
Okay, quenching. So that's when you're basically stopping the reaction,
Right.
usually by adding something to it.
So in this case, they were making a pretty complex molecule. It was a chloropropoxybenzoyl benzofuranol isoindole dione.
Wow, that's a mouthful.
It is, yeah.
Okay, so they were making this complicated molecule, and they had to quench the reaction.
Right.
And what was the problem there?
Well, the problem was that when they scaled up the reaction, the quenching process generated a lot of heat.
Ah, so it was like an exothermic quenching.
Exactly.
Oh,
And
yeah.
if they weren't careful, the temperature could get too high, and they could start to get decomposition of the product.
Oh, so it was like the reaction was still going, even though they were trying to stop it.
Kind of, yeah.
Okay, so how did they deal with that?
Well, they had to be very careful about how they added the quenching region.
Okay.
They had to add it slowly,
Right.
and they had to keep the temperature below 15 degrees Celsius.
Wow, so they had to really keep it cold.
Yeah, it was tricky.
Yeah, and I imagine that's not easy to do when you're dealing with large volumes.
No, it's not.
Yeah, that's really impressive that they were able to figure that out.
Yeah, they had to do a lot of optimization to get the conditions just right.
Right, because you don't want to, add it too quickly and have it overheat, but you also don't want to add it too slowly and have the reaction keep going.
Exactly.
Yeah, so it's a delicate balance. Okay, so that's another really good example, and I think it kind of highlights the fact that it's not just the reaction itself that you have to worry about.
Right.
It's all the steps around it.
Yeah, the workup is just as important as the reaction itself.
Yeah, absolutely. Now, for our last example, I wanted to touch on something a little bit different,
Okay.
which is this idea of continuous flow reactors.
Ah, yes.
And I know we've talked about this before on the show. I think it was back in season 6 when we did that deep dive on drug manufacturing.
Right.
But I thought it'd be worth bringing up again here because it kind of offers a different way of thinking about scale up.
Yeah, it's a very different approach.
So can you just remind us what continuous flow is all about?
Sure. So in a traditional batch reactor, you put all your reactants in, you let the reaction run, and then you empty the reactor and start over.
That's like one big pot.
Exactly. But in a continuous flow reactor, you're constantly flowing the reactants through the
So
reactor.
it's like a pipeline almost.
Yeah, kind of.
Yeah.
And the reaction is happening as the reactants are flowing through.
Ah, so it's not like a static thing. It's a dynamic process.
Exactly.
And how does that help with scale up?
Well, for one thing, it allows you to control the reaction conditions much more precisely
Yeah.
because you're not dealing with this huge volume of material all at once.
Right. It's kind of like you're breaking it down into smaller chunks.
Yeah, exactly.
Okay.
And that can help to improve the heat transfer and the mixing.
Ah, so you're kind of getting around those problems that we were talking about before.
Right.
That's really interesting. And then to scale up, you basically uh, just make the flow rate bigger, right?
Well, you can do that, or you can run multiple reactors in parallel.
Ah, so you're kind of like numbering up instead of scaling up.
Ex
Okay, that's really clever. So continuous flow is kind of like a whole different way of approaching this problem.
Yeah, it's a really exciting technology.
Yeah, and it's becoming more and more common in the pharmaceutical industry, right?
It is, yeah. And I think it has the potential to really revolutionize how we make chemicals.
Yeah, that's really cool. All right, so we've covered a lot of ground today. Let's take a moment to just kind of summarize the key takeaways here.
Okay.
So we've seen that scaling up a chemical reaction is a lot more complicated than just, multiplying everything by a factor of 10 or 100.
Right.
There are all these new challenges that you have to deal with.
Yeah, absolutely.
And one of the biggest ones is heat transfer.
Right. As a reactor gets bigger, it gets harder and harder to get the heat in or out.
Yeah, and that can lead to all sorts of problems like temperature gradients and runaway reactions.
Exactly.
And then there's mixing, which is
Yeah.
also really important.
Yeah, you have to make sure that the reactants are well mixed so that the reaction can proceed uniformly.
Right. Otherwise, you might end up with some parts of the reactor where the reaction is going really fast and other parts where it's barely going at all.
Exactly.
And then we talked about how the reaction kinetics can change when you scale up.
Right. The reaction might take longer to go to completion.
Yeah, because of all those heat and mass transfer limitations.
Exactly.
And then, of course, we looked at some real-world examples from OPR&D
Right.
where they had to troubleshoot all sorts of problems like that catalyst coating issue and that exothermic quenching.
Yeah, and those examples really highlight the importance of careful planning and experimentation.
Right. You can't just assume that everything's going to work the same way at a larger scale.
Absolutely not.
Yeah, that's a really, really good point. So I guess the overall message here is that scale up is it's a complex process,
It is.
but it's also a really important one because, if we want to make these important chemicals like pharmaceuticals and other materials, we have to be able to scale up the reactions.
Absolutely.
So it's definitely worth the effort.
Yeah, for sure.
All right, so I think we've covered a lot of good stuff today, but I want to leave our listeners with one final thought,
Okay.
and that is this: we've talked a lot about the technical challenges of scale up,
Right.
but there are also a lot of other factors that come into play when you're trying to, take a reaction from the lab to commercial production.
Oh, yeah.
Like, safety regulations, environmental concerns, cost considerations, all sorts of things.
Absolutely right.
So I guess the question for our listeners is, what are some of those other factors that you think are important to consider when you're scaling up a chemical reaction?
It's a really good question.
Yeah, it's not just about the chemistry; it's about the whole picture.
Right, the bigger picture.
Yeah.
It's a very multifaceted problem.
Absolutely. All right, well, that's all the time we have for today. Thanks so much for joining us on the Deep Dive,
Thanks for having me.
and we'll see you next time.